Hello and welcome to my talk, Fast Inference Applying Large Models on Small Devices. My name is Sebastian Buschjäger. I'm a PhD student in the University of Dortmund at the Artificial Intelligence Group. Professor Morik is my supervisor, and I think some of you know her personally, so she told me to send my regards. I'm doing my PhD in the Collaborative Research Center 876, and this is a huge research center with different application fields and different researchers from different fields. But the main theme is machine learning in the context of resource-constrained devices, or quote-unquote small devices. And what I want to talk about today in this talk is the application of pre-trained models on these small devices. And just to start this off, I want to give you a quick example why this is important. We all hope for that at some point we have an autopilot feature or self-driving cars in general, and this might take a few years still, but from what is understood today is that deep learning will play a major role in this kind of technology. And Tesla is a little bit more outspoken about how they implement their autopilot feature, and what they use is pretty much an end-to-end deep learning approach where they have trained a deep neural network that takes input images from the street and then processes those to produce steering outputs. And now you will probably say, well, deep learning, this is very resource hungry or energy hungry technology, so maybe this will take a couple of miles of the mileage of my battery powered car because I need to run this feature. And indeed, you're completely right. Deep learning is very energy and resource hungry, and this is something the engineers at Tesla also know, of course. So what they came up with is a custom inferencing chip, which is pretty much an FPGA on steroids that continuously runs this deep neural network over and over again on all the different inputs all the time while driving. And this inference chip requires something in the range of 60 watts to be powered. And so the question for me was, well, we're driving lots of cars across the entire globe, so what is the environmental impact of using this feature in all those different cars across the entire globe? It's pretty difficult to get some hard facts on how much distance is actually covered by car on the entire world. So I'm just looking at Germany here because we do have some numbers on that. And I found a study from 2018 which estimated that all the personal cars in Germany combined traveled something in the range of 630 billion kilometers. And so the question for me is now, what is the environmental impact, or what is the energy consumption if we would use the autopilot feature from Tesla's cars in all those different trips? And to do so, we need to estimate the time, how long those cars traveled and how long this feature would be enabled. And we can do so by using the average speed of a personal car. And if you want to, you can stop the video right now and have a quick discussion on that. It was debated here and there in our chair, so it might be interesting for you to also do that. If you don't want to do that, then I can give you the numbers now. And what I found out, it's 45 kilometers an hour, which kind of makes sense given that most inner cities have a speed limit of 50 kilometers an hour, and there are of course also traffic lights and pedestrians and all that stuff. So we cannot travel the highest, the fastest all the time. So the average is 45 kilometers. Now combining these three numbers gives us a value of 0.8 terawatt hours. So that means that using the autopilot feature from Tesla's cars in all those different trips, while driving roughly 45 kilometers an hour, uses 0.8 terawatt hours in a given year. And this is a huge number, and I don't know what this huge number means, to be honest. I know what a couple of watts mean, but I don't know what terawatt hours mean. So I looked it up, and I found out that the largest run-of-the-river hydroelectricity plant that we have in Germany also produces this amount of energy in a given year. So put differently, we would need an entire energy plant in Germany to power this one feature across all the cars we have deployed at the moment. And so it's pretty clear that we will never, or hopefully never, use an entire electricity plant to train such a deep neural network. But as soon as we deploy it in the real world, we have this massive parallelism and this massive application over and over and over again that we really need to watch out how we do the inferencing. And this suddenly becomes very, very resource intensive. Okay, so now I talked about small devices, then I talked a little bit about 60 watts, the inference chip from Tesla uses. So what do I mean with small devices? So basically everything which is a Raspberry Pi or smaller. So Raspberry Pi, this is an embedded system, probably most of you know this. It has a couple hundred megabytes of RAM, maybe a gigabyte, and it uses something in the range of 80 milliamperes to 260 milliamperes. And these 260 milliamperes roughly equates to 2 point something watts, 3 watts, depending on what you run on the Raspberry Pi. And so this is kind of the biggest device we're looking at, and of course there are many smaller devices down to a couple of kilobyte, which just use a couple of milliamperes. So this is really low power devices here. So when we talk about the energy consumption, then we are bound by the physical laws, of course, and that pretty much means that the total energy we require for a certain computation, it's the energy per time times the time we do this computation. And in the context of inference, this means that we have the power consumption of the hardware times the inferencing time. So put differently, it is a combination between the hardware we use and the model we execute. So if we can have very potent hardware which uses a lot of power, for example a GPU which uses like 200 watts, but then the model execution is just a couple of nanoseconds, and so the total energy we require might be less than using less powerful hardware, maybe Raspberry Pi which just uses 1 or 2 watts, but then the model execution takes a couple of seconds. And so we really have those two things where we can play with and see how to optimize our execution environment. Now, approaching inference, there are in general 4 different ways we can do that. And the first approach is to take the pre-trained model. So we have a data mining problem, and there is a data scientist or a machine learner, and he or she takes the problem, tries a couple of different models, and then at some point says, oh, this is the pre-processing, and this is the model, and this is what we want to deploy now, and this is what we should use. And then this is given to an embedded systems engineer, and the engineer will then try to make it fit and make it work on a small embedded device. And then maybe he or she will tell the data scientist, well, this doesn't fit, it's too big, we need to change the model. And then we start to change the model to make it fit the small device. I guess the most straightforward example of this is decision tree pruning. So we train a huge decision tree, and then we start to prune away certain parts of the tree. And usually we do that to combat overfitting, but of course this also helps us in the resource consumption, because the tree is suddenly getting smaller and smaller, and thus taking less memory and having smaller execution times. Now the second approach would be to train an entirely different model from the beginning. So if I know that I only have a couple of kilobytes of RAM available, then I will hopefully or probably only train a model which uses a couple of kilobytes of RAM. So maybe it's not a good idea to start with a huge deep learning, I don't know, ResNet or BERT model or something like that, but maybe go for a linear regression or a decision tree or KNN or something like that, because we know that this will fit the small device. Then third, and this is pretty much orthogonal to the first two approaches, we can use the hardware we have given in a different way. And there a lot can be done with using caches efficiently, and we can really reduce the execution time of a program if we use caches in a smart way. But we can also use other special hardware features. For example, if we have a GPU available, we can use that for processing and stuff like that. And fourth, we can come up with new chips and entirely new ways to process information. This is something Google has been doing now with the TPUs, and there are a couple of other competitors now out there, which are also available at the edge, so to speak, so for small embedded devices. And I'm not going to talk about 4. I think this is a little bit too far, this is out of scope here, and I'm mainly going to focus on 1 and 2. And in the later parts of the talk we are briefly talking about 3, and I will point you to a couple of papers from our working group, but 1 and 2, this is what I want to focus on in this talk now. And what I specifically want to focus in this talk are tree ensembles, and more specifically random forests. And I want to do so for 2 reasons. So first, I think deep learning is a very interesting and nice technique, and it has very good performance in some areas. But it is, as it is, very, very resource hungry, and sometimes it's simply impossible to put it on a small device. So we have to look for other methods if we want to do machine learning on in these really resource constrained environments. And here, random forest and tree ensembles in general strike a very good balance between performance and resource consumption. So we can change trees, we can remove trees from the forest, we can change the training method, and suddenly make them very adaptable to this kind of scenario. So I really like them a lot. And second, it's very difficult to give you a comprehensive overview of deep learning techniques because there are so many out there, and it's very difficult to keep up with those. And with random forests, I personally know what I'm talking about, so this is a little bit more in my comfort zone. But of course we will talk about deep learning a bit in the end, if this is what interests you. So yeah, change the model after training. And now, as I said, assume you have a random forest or any tree ensemble given to you. The data scientists you trust says, well, this is a great model, take it, it's nice. It contains, let's say, 1024 different trees, and you try to put it on your small device, and then you noticed, shit, it doesn't fit, it's too big. And then maybe the most natural idea here is to say, well, it's a random forest, and random forest with 1,000 trees is probably better than one with, let's say, 32 trees, but 32 trees is still better than having none. So maybe let's try to fit 32 on the small device. And so this is what you can call ensemble pruning. So instead of having this large, diverse forest with lots of different trees, you try to select a couple of those which preserve the diversity in your forest and preserve the performance, but uses much fewer memory because you just selected a few trees. And we can write that down more formally. So you have your tree ensemble with m trees. Each tree hi gets a corresponding weight w, and this weight w is either 0 or 1, and 0 meaning we don't select the tree, and 1 meaning we select the tree. And now the task is to minimize the loss function here over this w vector, so that the entries in the w vector are at most k of those are equal to 1, and the rest is 0. So we exactly want to select k trees from our ensemble, and k should be much smaller than m, and this is a hyperparameter we choose. So m might be 1024 and k is, let's say, 16. And then we want to minimize this loss function over either the training data we have, this might be the data we used to train the tree originally, or it can be a non-related third so-called pruning set, which is just used for the pruning here. Now we can look at literature, and there is a method which is nearly 25 years old, and it has been originally published in the context of AdaBoost and these boosting kind of models, but you can use that for random forest as well. And the idea is as straightforward as it gets in this context. It's a very simple greedy method where you start with no tree, so you have not selected a tree yet. You rank all the trees in your ensemble by their error, and then you pick this one tree which has the smallest error. And this is what is written down pretty much here in the first 3 lines. So, and then you start to iteratively add one tree to your ensemble by minimizing the overall ensemble error. So you pick the first tree, you check the error, then you pick the second tree, check the error, and so on. And in the end you pick this one tree which results in the smallest ensemble error. You repeat this process k minus 1 times, so in the end you have k trees selected. This is a very neat algorithm. You can implement that in Python or any other language, and it pretty much also needs like 10 lines of code, so that's nice. And then we can do experiments with that. And so what I did here is I trained a random forest with 265 trees, where each tree in the ensemble has a different number of leaf nodes. And so here in green, the trees have at most 64 leaf nodes. And then here in this red, purplish color, pink actually, in this pink color, it's the trees have at most 128 leaf nodes, and then this purple, it's 265, and then 512, 1024. The solid lines, this is the ensemble we get when we apply reduced error pruning with k equal to 16, 32, 64, 128, and so on and so forth. So I sampled different numbers for k here. And the dashed line, this is when we randomly select 16, 32, 64, 128, and so on trees from the original random forest. And there are a couple of interesting aspects we can see here. So first, and this is pretty much in line of what we would expect, the more complex the base learners are. So the more leaf nodes the tree have, the better the accuracy is. And we really see these nice different levels here. Then second, and this is a little bit more interesting, we see that pruning actually improves the performance, and it improves the performance even compared to the original random forest. So you can see here the original random forest with 265 trees has an accuracy of something in the range of 82 or 81 point something, and when we select only 16 of those trees, then we suddenly have a better performance. And there is a real gain here to see. What's interesting, and that's the next thing, this gain reduces the more complex the base learners get. And in fact, if we are just interested in the best random forest with the best accuracy, and we don't care about memory or resources at all, then we would probably pick this one here, which seems to have the best overall accuracy. So reduced error pruning reduces the memory consumption. This is quite nice, so this method actually works. And as a bonus, we kind of get an improved accuracy if the base learners, if the trees are not as complex as we would usually train them. So if we have small trees anyway, then pruning suddenly makes a lot of sense. And so this is a weird effect. This is something you wouldn't really expect from this kind of algorithm. And so my first idea, and this is maybe something you're also thinking about now, is that, yeah, this is reduced error pruning. This method is 20-something years old, so maybe we didn't come up, maybe we came up with a better method in the meantime, and we should try more recent methods. And this is exactly what I did. And you can find different hierarchies of methods or different types of methods which perform ensemble pruning. Ranking, clustering, mixed integer programming, ordering based. And I don't want to talk about these different taxonomies in detail here. This would lead a little bit too far. I just want to mention I implemented all these different methods in a Python library called pipe pruning. It's available on GitHub. It implements, I think, 16 papers now, plus some additional methods you can play around with, and really enables you to quickly try out different pruning methods and implement your own if you want to. These are all extendable classes, and you can put in your own loss function if you're interested in something like that. So using this library, we can redo this experiment from the beginning and check if more recent methods maybe perform better. And this is what I show you here. These are just a couple of methods now to not overload the slide. And here in bold, you see the best performing method. And so the first thing that we see is reduced error pruning is a pretty good competitor. So it's still one of the best, or in this case here, the best method. And it's only outperformed by IC, which is a method from 2017, when we look at more complex base learners. The second thing which happens is that the same effect we just saw is also present here. So if we look at a random forest with small base learners, so only 64 leaf nodes, we see a performance gain of 1 point something percent, 1.3 something in the range. Now if we look at base learners which are much more complex, so they have up to 1,000 leaf nodes, there is not much to gain here. In fact, random forest now is a little bit better. So if we look at the performance of IC or IE in this case, it actually increases the performance by roughly 1%, but it's not as stable as it is for the smaller complexities. So the general gist is the same. So the more complex the base learners are, the less effect we find from ensemble pruning. We can just randomly train a random forest with, I don't know, 16 trees, and then we're good. All these experiments now I showed you have been performed on one data set, and of course you can think about doing this on another data set. And in fact I did that. I tried it on 20 different data sets, and the general scheme will always be the same. So ensemble pruning really helps if you have not complex base learners, so anything in the range of 64 to 128 leaf nodes, depending on your data set. And then at some point, if your data set becomes more and more complex, if the trees for your data set become more and more complex, then you can train a random forest from scratch, and you're usually good to go. And that kind of makes sense if you consider that all those pruning methods work on the same random forest. So we're just selecting trees from this forest, and we're not changing the trees, we're not doing anything. So maybe this is an inherent limit we are reaching with the base random forest we have given, and we can't really improve beyond that because all methods use the same random forest. And so this brings me to the second point, can we train a different model from the beginning? And more concretely, can we directly train a small and a good random forest? And so just to give you a little bit more context and a little bit more notation for that, so the basic idea is now to train a small initial random forest, which we know will fit on our small device. So we know we can store, let's say, 16 trees with up to a tree depth of 10 levels, which means something in the range of 1024 leaf nodes, and this is what fits on the small device we have given. So we can train this, and then we will refine the trees in the forest. And so to do so, I now have some more notation for you guys. So this is a simple decision tree. I guess you all know how this looks like. And the decision tree performs these axis-aligned splits. So we start the root node, and then we compare a feature, in this case F0, of our observation against the precomputed threshold T0. And depending on this outcome, so depending if F0 is greater than T0, then we will visit the right subtree, or if that's not the case, we will visit the left subtree. And we continue this until we reach a leaf node. And the leaf node, this is just contains simple constants. Usually these are probability estimates from the data we have. Sometimes these are counts, but from a mathematical point of view, this is just a vector with C entries, and where C is the number of classes. And the idea now is that optimizing these thresholds, this is very complicated. This is something very complicated if you have a tree or forest given already. And it can change the entire structure of the tree if I change one of those thresholds here, and then I need to reorder the subtree, and this is all very difficult. So my first basic idea was to let the to keep the structure and not change the thresholds or split values. Those can be efficiently computed with a top-down greedy algorithm, so CART or ID3 or whatever you want to use here, but to only change the prediction values in the leaf nodes. So we keep the entire structure of the tree alive and just work on those leaf nodes here. How can we do that? We can do that with gradient descent or stochastic gradient descent. I assume that you also know this algorithm, but as a quick reminder, I'm just telling you about it. So the basic idea is that I want to minimize a loss function L, which receives the predictions of our model and the true labels. And the predictions of our models are parameterized with a parameter vector of theta. And now we want to update this theta vector with small steps using an estimation of the true gradient of this loss function with respect to theta. And why is it an estimation? Usually this B here would be over all the samples in our training data, so it would be S. But since it's stochastic gradient descent, we simply sample a couple of examples or maybe a batch of examples and then compute this gradient on the batch and then perform the step using this estimated gradient. We can use the entire data set here as well. In that case, this would become gradient descent. But stochastic gradient descent is usually much quicker, and so we like this algorithm. Yeah, as I said, split values and thresholds are quite difficult to optimize because they kind of rearrange the structure of the tree and have all sorts of other nasty side effects, so they don't have proper gradients, and we really need to make sure that it works in this kind of a framework here. So I'm just focusing on refining the labels in the leaf nodes, and so my theta vector becomes all these different vectors with the C entries. Yeah, and that's pretty much the entire algorithm already. So what we do is we train an initial random forest, and we set K and NL, so the number of number of trees in the forest and the maximum number of leaf nodes in the trees. We set those to sane values, which we know result in a forest which will fit on a small device. So this might be 16, and then this might be only 8, or we say, okay, let's take a lot and let's take 1,000 trees, but then it's maybe just 2, and there's pretty much decision stumps now. So we choose those 2 values to fit the small device. And once we have this forest, then we simply start to update or refine the leaf nodes using stochastic gradient descent. And the interesting part about this is, in a random forest, we do not have any interactions between the single trees. They're just trained independently from each other, so that makes this a very appealing algorithm. But also this wastes a lot of potential because we cannot efficiently utilize interactions between trees. And what we do here with the leaf refinement, we reintroduce this coupling between the trees into the optimization again, because the loss function takes the entire prediction of all the trees combined. So there is a coupling here already between all the different trees, which hopefully leads to better trees with smaller memory consumption. Yeah, and this hope is actually exactly what's happening. And I brought you 2 different plots here. I just want to quickly talk about. So let's start with the left side here. So in the beginning, what we see here is the accuracy over different model sizes in kilobytes. So in the beginning here, we just have something in the range of 10-ish kilobytes, a little bit less, 1 kilobyte even. And in this case, we can barely fit a random forest on our small device. And this is maybe 1 or 2 trees, depth 1 or 2, just a few decision nodes basically. So most methods don't really have great performance here, and they really start to get better over time once we have a little bit more memory available. And this is 1 megabyte here, and I stopped this plot at 1 megabyte because this is what most embedded systems have available. But we could continue this plot to 100 megabyte to gigabyte, and we would see a similar trend with some diminishing return property towards larger models. So then we can look at this middle part here, and we can see here in purple that random forests, which are trained and then refined with leaf refinement, have better performance. So they have a better accuracy for a given model size. So this is really what we hope for, to have a good and small random forest. And then in the end, if we get to even bigger models, then the performance seems to converge against a common performance or accuracy, which kind of makes sense because we're still talking about additive decision trees here, or decision tree ensembles, and there seems to be an inherent limit of how good we can get with those models. And of course, there's also an inherent limit for the data set, which seems to be reached at this point here. There's another type which I observed during my experiments. This is another data set here. We have the same effect in the beginning where we don't really learn much at all. And then we have this effect that the leaf refinement actually improves over the performance of the other methods. But now we are actually having a much, much better accuracy of around 8% in this scenario here than the other methods have. So in this setting, leaf refinement is really giving us a much, much better accuracy compared to the other methods. So this is really, this is not even what we hope for, this is even better what we hope for, so to speak. So leaf refinement does not only have a better memory accuracy trade-off in this in-between space here, but it can also converge against a better solution. And this is due to the coupling of the different decision trees. So these were two data sets, and we can then do a statistical analysis using critical difference diagrams. And there we can see that random forest with leaf refinements will actually give you the best performance and only share a click with the IC method. But as you can see, this is in most cases it's the best method on all the different data sets I tried. We can also do a use case study on Raspberry Pi Zero. And what I did here is I limit the maximum amount of memory to 1 megabyte for the entire binary in the end. So there were other parts which were loaded and other parts of the program which were required to make this run, and I wanted to have 1 megabyte in the end for the entire program. And there you can see that random forest with leaf refinement has 91 point something% accuracy, which is the best method, while being the third smallest binary in the end. So DREP and CA also have very small models. And the funny part is, for example, for CA, I couldn't find a smaller model which was better, which is below 1 megabyte. And the same goes for the other methods as well. So leaf refinement really improves the accuracy and the memory consumption here at this point, which is super interesting. I implemented all these experiments, of course, using the Pi pruning library I showed you earlier. And so you can look at those on GitHub as well. But what might be even more interesting if you're interested in this kind of stuff, we do have an archive paper called Improving the Accuracy Memory Trade-off of Random Forest via Leaf Refinement. And this paper pretty much contains everything I just talked about. So all these experiments with pruning and how pruning works, why does it work, all this stuff, and leaf refinement as a new method to improve the accuracy, and all those different examples and this analysis here. So talked about changing the model and training a different model, and then of course we can also use the hardware in a different way, but this is something I don't want to talk about here. And we have published a couple of papers on that as part of the Collaborative Research Center, and I will just point to those papers here, which are all either from my side or from a couple of my colleagues, and this is also joint work, especially with the Chair 12 for Embedded Systems at the TU Dortmund University, with Janjia Chen and Quan Sun Chen. So they really helped us here with data layouting and all this stuff. So if you're interested in this kind of stuff, you can, I will give you another link at the end of this talk, and there you can find all those different papers and how to apply these different techniques. What I want to talk about in the last part of my talk is putting all this stuff together. And so what I talked about now a lot is models and algorithms, but I didn't really talk about implementations. And there is an interesting paper from Kriegel et al. From 2016, which roughly poses the question, are we comparing algorithms or are we comparing implementations? And in the context of inferencing, the implementation takes a very special place. So the implementation must respect and know any of the specifics of a model. So if I come up with a very sophisticated linear regression which only uses, let's say, 0 and 1 as coefficients, then I could theoretically implement these coefficients using Boolean values. But if the implementation doesn't do that and just uses float, well, then it kind of defeats the purpose of having this very sophisticated linear regression. So the implementation must know the model. At the same time, the implementation must also know the target hardware. So if I have, for example, SIMD instructions which consume multiple data points and execute the same instructions on these data points, then oftentimes they only work with specific data types. And they don't work, for example, with Boolean data types, but only with char or int, bytes, something in that range. So maybe it might be better to implement this very sophisticated linear regression not using Boolean values, but using integers or chars or whatever, because then we can utilize those SIMD instructions as well. And third, and this might be the most frustrating part for us machine learner, an implementation should be kind of flexible to new methods and new models. So in the beginning of my PhD, I tried to keep up with deep learning and neural network pruning and this area, and this was just about to start when I started my PhD, so it was a good fit at that time. But to be honest, at some point I couldn't keep up with it anymore. There were so many different new papers published from different groups, different people, that's very, very difficult to not only read those papers, but to actually implement them, try them out, and see how they work. So any implementation should be flexible enough that we can quickly try out different ideas for maybe very new, weird models we are just designing, or other weird hardware we have, something like that. So yeah, the implementation must be really, really flexible. And as an answer to all these questions, I at some point started to implement a tool called FastInference. And this tool is basically a model optimizer and code generator with a target to embedded systems. And this tool has these three things in mind I just talked about. So we try to separate optimizations and implementations as much as possible, so you can focus on one of the two things if you're only interested in one of the two things, but you can also combine them if you're interested in both. And this kind of leads to rapid prototyping, where you can quickly implement new ideas into this existing code base while utilizing what's already been implemented. And this is maybe the one most important aspect in all of this. This is a code generator, and code generators naturally generate code from a machine for a machine, so we don't really take much time to make this nice and readable. And I try to put in some effort to make the generated code also readable, which helps collaboration, because you can send people the generated code and tell them, okay, you need to change a couple of lines here, and then your model should work on your weird new embedded device you have. So this is, personally for me, this is really important to facilitate working together on these kinds of problems. Yeah, so this is of course available on GitHub, as you probably guessed now. It's called FastInference, and you can find it in this link. You can also Google it. If you Google it a bit, you will find it. I don't think it's the first hit, because FastInference, this is something a lot of people are talking about at the moment, but you will find it. Otherwise, just send me a mail and I will give you a link. And we have used this tool in a couple of different papers so far, and of course in the paper I just talked about, with improving the accuracy memory trade-off, a couple of other decision tree papers from the beginning. This is when I started to work on this, but also on physics problems with deep learning and FPGA. So this really shows how flexible this whole approach is. We also have deep learning now integrated in some parts of this toolchain, and FPGAs as a possible target. Yeah, so how does it work? I just want to give you a quick overview. So the basic idea is you train your model in the framework of your choice. So in deep learning, this is usually TensorFlow or PyTorch, and then you can export your model in an ONNX format. This is the open exchange format for neural networks. And we can read this type of file. We can read a computation graph from this file, or if it's a classic method, so a random forest, decision tree, whatever, then we just expect a JSON file. We read this file, so this might be, for example, a representation of a decision tree. It has 45% accuracy. I called it decision tree. It has 5 classes, and the split value is on feature 1, and the split is minus 0.14 something something. And then the right child has also a split, feature 9, split value minus 1 point something, and so on. So we take this file, read it into an internal data structure, and there is indeed nothing fancy going on here. This is just a holder, a placeholder for all the different nodes in the tree. And then and this is the more interesting part, we perform optimizations based on this model. And so, for example, this is the pruning part. So here we create the pruner, and then we apply the pruning, and then we return the prune model. And this is also what was the most difficult in implementing all this stuff. I tried to make sure that the user can just focus on what he or she wants to implement. So the FastInference tool will try to look for Python files in specific paths with specific functions and try to call these with the correct arguments. So what you can really do is you can simply put in a Python file under a specific path, and then FastInference will try to play nicely with this and interact with it in an interesting way. Yeah, the same goes for the backend. So for the backend, we use templates and a template engine to generate different pieces of the source code. And what you will get in the end is one huge line of C code in most cases, which implements the model. And for example, this is a decision tree in its if-else structure. So if X, and then this node.feature will be replaced by the template engine, and node.split will be also replaced by the template engine with the corresponding split value. And so this code snippet here is pretty much everything you need to implement the decision tree. Then FastInference will take care of loading all those templates and actually using them. And what it will look like in the end is something like this. And you remember maybe this is the first feature we looked at, and then we have the comparison, we have the 9th feature, the comparison, and so on and so forth. So this is really one huge chunk of C code. Yeah, this code generation in the end. This is actually not the hard part, but making this code generation play with the optimization and the different kinds of models and combining all those into one coherent tool, this is the difficult part actually. But it enables us to do a couple of interesting things. Yeah, so for example, what we can do now is that we support more obscure models. So for example, there are models called Binarizing Networks. These are special types of neural networks which use -1 or +1 as their weights. So there are no floating points involved. And since -1 and +1 can be mapped to 0 and 1 on the hardware level, we can actually implement the entire forward pass of the neural network in Boolean logic. And so what you would do is you would apply the XOR operation over and over again, and then at some point you need to count how many zeros and ones you have in a given bit string, and this is called the pop count operation. So yeah, what you can do is you can implement the entire forward path of a deep neural network, which with these kinds of weights in Boolean logic, and as far as we know, there are 2 implementations available, and FastInference is one of those. So I think that's pretty cool, and this is what we used on FPGA as well, for example, so this is very interesting stuff. We can do more crazy stuff with this as well. So maybe some of you know there is a tool called Hex, and Hex pretty much defines a programming language akin to Java or C#, which can then be compiled to other languages. And so what I just did for fun, I implemented a backend for linear regression in Hex, and now we can have a linear regression in Java, JavaScript, PHP, some C dialects, and I think even Flash, because that's still supported from, I don't know, 20 years ago. So yeah, this is interesting and fun, but the performance is probably quite bad. I mean, nobody would use PHP to run a deep neural network or linear regression. What is more interesting, and even more recently, I started to integrate some parts of the LLVM compile stack into this tool as well. So at some point in the last 2 years, the LLVM people, and if you don't know that, these are the people who came up with specifications for the Clang compiler and implemented it. They also came up with a specification for an intermediate representation language which can be used for machine learning. And they are really looking at these tensor operations and computation graphs, which we often find in deep learning, and try to efficiently map those to tensor operations, which are then basically compiled to either CUDA code or to C code or other types of code. Yeah, and I recently implemented parts of this, so we can now output these MLIR dialect, it's called in this case, and we can take that and we can put it into IRI, and IRI, this is a tool from Google, which then executes these computation graphs for you. So this is yeah, the classic meta compilation approach you would do. You have some representation of a computation graph in O and X, you do some optimizations on that, you output then this intermediate representation, and then you have a backend which actually executes this intermediate representation. And so currently this IRI supports Vulkan. This is the successor for OpenCL, and bare metal programming in 2 different ways. And this is what I leverage from Google basically, but what we can do now is we can also program decision trees in this environment as tensors basically, and then utilize all these nice interesting backends here. Yeah, so this brings me to the end of my talk, and so the one most important part of this talk for me personally is energy is an important aspect, and even non-deep learning methods require a lot of energy. And I do have a second example where I calculated the energy consumption of gradient boosted trees in the context of ranking. I didn't show you this because the numbers are not, I need to do a lot of assumptions basically. But for all machine learning methods basically, we have the same trend that we as machine learning practitioners usually look at training times because this is what we do every day. And we are super happy if training is twice as fast. But if you deploy these models into the real world, and then suddenly they scale in such a weird and massive way that they require more energy for the continuous application than for the training. And so this would be my main takeaway from this talk for you guys, that well, energy is important, and we have to look for the energy consumption of model application if you really want to have resource efficient machine learning. How can we do that? We talked about that a little bit. We can change the model after training, and this is there I showed you ensemble pruning. We can train a different model from the beginning, for example a random forest with leaf-refinement. We can use hardware in a different way, and I didn't talk about tree framing or node swapping, which are techniques to use the cache more efficiently, but they're implemented in FastInference, so you can check it out. We can use different hardware, of course. This is something to be done, and maybe I'm not the right guy for that, but maybe you have some interesting ideas on that and we can discuss it. And then we talked a little bit about FastInference, and the main message here is that the implementation and the optimizations, they both must go hand in hand if you want to have efficient machine learning. So, I mean, we can come up with the newest and craziest optimizations, implement them in Python, but at some point we should check, well, do these optimizations actually help us down at the C level or sampler level or whatever language we use to implement these machine learning models in the end, right? So FastInference is a tool to bridge the gap between both worlds. Thank you.